Hello students, now we shall continue the properties and questions on ideals from previous lecture. In previous lecture we have discussed some properties and some questions on ideals. So today also I should continue the same. So there is one question: for any element A in R, let Ra equal to, that can be expressed as small ra, where small r, which is a member of ring any element of R there, show that this Ra is a left ideal of R there. So now let us take, we need to prove that Ra is satisfied under closure under addition, as well as this is for any element which belongs to, that is R belongs to R and any element belongs to Ra, then it needs to be again these two conditions for ideals are left ideal. So then we can say that this Ra is a left ideal of R. Let us take two elements which are the members of this Ra. That Ra we have defined like this here. And this, let you take that X is R1A and Y is R1, R2A, where R1 and R2 are the members of a ring R there. Now we can see the first properties of ideals are left ideal. So then we have there, it is closure under addition, that Ra is closure under addition by taking X minus pi equal to R1A minus R2A. That's A is common term. Again you can keep it in the left of this, because since R1 and R2 belongs to R, so that R1 minus R2 is also a member of R there. So then it obviously it is R there, so that this X minus Y is also a member of Ra. Then definitely it is satisfied, this Ra is closure under addition. And also in the second property of ideal there, especially left ideal or right ideal there. So for any R belongs to R there, so Rx you can take it elements, that is x1, x we have taken that R1A, so that we have taken that R into, that is x is there. So then we have to take it as good as C, that keep remember here, sorry it is R is not there. So R1 into R into R1 into A there. And then since R and R1 are belongs to the members of R, so definitely it is RA there. So that is what there, this Rx is also that, Rx is also member of Ra. Since Rx is also member of Ra, and then also this property, this Ra is satisfied closure under addition, definitely it holds good, that is the, this Ra is a left ideal of R there. So that R into R1 A is member of R, then Rx is also member of Ra. So hence Ra is left ideal of R there. In the second next question, so prove that intersection of the families of left ideals of a ring R is again a left ideal of R there. Now let us take A alpha, where alpha is belongs to the indexing set I there, because it is an indexing set I there. So be a family of left ideals of a ring R there. Now we have to show that this intersection of family of all the left ideals of R, where that suffix alpha which is the belongs to, that is the indexing set I there, is a left ideal of R there. So this A alpha, intersection of A alpha, alpha belongs to I, this has to satisfy both the properties of that closure under addition, as well as this is the, where the elements belongs to, that is the one belongs to, that is the, this intersection of this A alpha, and also belongs to, that is the ring R. So definitely that second property is also, that is the, also holds good, that this intersection A alpha A alpha, where alpha is member of indexing set I. So then these two satisfied the both the properties of left ideals. Just we can see that let xy is member of intersection of A alpha, where A alpha is member of indexing set. So since we have this, definitely see that x minus 5, this is also member of A alpha. Once if it is a common term, definitely it would have been A alpha there. For each alpha is member of indexing. Since each A alpha is a left ideal of R, thus it has to be definitely this A alpha is satisfied the closure under addition there. So that is what we have. So then it is for each alpha it is satisfied that closure under addition. Then intersection of A alpha, alpha is member of I, this also satisfied, that is the closure under addition. Now second property you can take it, let element of R, that is R belongs to R, and any element which is the member of this intersection of the family of all the left ideals where of alpha, that A alpha, alpha belongs to I. So then it is what here, intersecting element is nothing but which implies x belongs to A alpha for each alpha. Since A alpha is the left ideal of R, so then Rx is also, that is definitely A belongs to the member of A alpha for each alpha. Then it is also member of intersection of all the families of left ideals of A alpha, alpha is member of that. Hence intersection of all the families of A alpha where alpha is belongs to the indexing set, it is also left ideal of R that. So now we shall see that another question there. If I is an ideal of R and A is a subring of R, then show that I intersection A is an ideal of A there. See, keep remember, I is an ideal of R, A is a subring of R that. So then we need to show that this ideal of R and subring of R, so those two intersection, again it is an ideal of A there. So then ideal of subring there, subring of R there. Now let us take two elements which are the members of these two intersection of ideal and then subring that. So then intersection, so that just these two member of I as well as member of this A also there. So this satisfied, this I is satisfied under closure under addition since I is an ideal of R. Since A is a subring of R, this is the common property in the ideal and subring. So this A is also satisfied under this A is subring, which also satisfied, which is closure under addition. So then anyway it is and that, so that definitely this I intersection A, intersection of ideals and subring, is again satisfied, that is closure under addition. So then we can see that you can take it any, let us take X is an element of intersection between ideal and subring, and you take it any elements of A is an ideal there, which is a proper subset of, that is the R there, proper subset of R there. So definitely it would have that it is a member of I as well as member of A there, because it is a common there. Thus you can take it Ax is belongs to I, since I is an ideal of R, because A is an element of A there, and also Ax is also member of A also there. So then definitely it would have that Ax is member of intersection between ideal and subring there. Similarly, we can prove that Xa is also member of intersection between the ideals and subring there. Definitely, once these two properties of ideal, so that definitely this intersection of I and A, this ideal and this, again it is a ideal of A there. So another question there, here we have there, if R is commutative ring and A is an element of R, prove that L of A, that can be expressed as L of A is Xa equal to 0 there. Is product of any element of R and any element of this A R there, commutative ring, then which gives product is 0, this L of A is an ideal of R, we need to prove that. Now let us take T1 and T2 are the members of this L of A there. It means what we have a given, since it is xa equal to 0, so that T1 is x1a equal to 0 and T2 is also x2a is 0. So that L of A, it satisfied the closure under addition there. T1 minus T2, that implies, so that which gives, that is x1a minus x2a. By taking x here, since this here, keep remember x1 minus x2 into a there. So since a is non-zero, definitely it would have, that is this T1 and T2, this is the member of LA there. So it is the LA is satisfied, that is closure under addition. Now for you take any element of commutative ring R, so then we take it A is member of R. So then also we have a T1 is member of this LA, that means XA. So then which we have that RT1 equal to, that is R into x1a, that equal to R of 0, because x1a is 0 there. Because it LA which have that defined that xa is 0, so that x1a is also 0. So definitely it would be proved that. So then Rx into x1 into a equal to 0, because since it is 0, so this is 0. So since R is member of R, it is, and x1 is also commutative properties of that commutative ring, so then Rx1 is also member of R then. Thus Rx1 into A is 0, that means Rt1 is also member of LA. That means L of A is the left ideal of R there. Again, for R is member of R and T1 is member of L of A, so then T1 R equal to Rt1 and T1 R now. So T1 is, as we know, that x1a equal to R, and x1 as we know that it is L of A is, that is 0, x1 xa equal to 0. So then which we have, that is what here, x into a R, that is equal to, because since R is commutative, AR equal to RA there. So x1 R into A, just by taking, that is R1x we can have there, and this again we want to made it like this is the definition of LA. So that since x1 R is member of R, and definitely this x1 R into A is also member of LA, that is T1 R is also member of LA. So thus L of A is the right ideal of R, hence it satisfied both the properties left as well as right. Only it is the common property of ideal is, that is a closure under addition. So then which is L of A is an ideal of R there. So another question, let I be an ideal of R, then show that Ri, it is, see that what that Ri can be defined here as X, where X is member of R, it is ideal of ring there. Rx is member of ideals, so then for any R belongs to R there. So then now we can have there, it is again an ideal of R containing I there. Let us take x1 and x2 which are the members of Ri. That is x1, Rx1 belongs to I and Rx2 belongs to I, for any R belongs to R ring there. So then first property of ideal there, Rx1 minus Rx2, which is also write it as R into x1 minus x2. Since x1 minus x2, this is the property holds under addition there in R, definitely it holds good in ideal that also there. That is R into x1 minus x2, which is member of I there. For x1 minus x2 is member of R, it is closure, and then that is R into x1 minus x2 is member of I, then it would implies that x1 minus x2 is member of Ri there, because since we have defined that Ri as it is. So now for R1 is member of R and x1 is member of Ri, so Rx1 is member of I there, for any R belongs to R. Similarly you can take it, see that R1 into Rx1, that equal to R1 into Rx1. So then because R1R is member of R, then it implies that is R1 into R x1